Hi, Jeremiah. I'm doing well. How's your week been? Been good?
Yeah.
That's good. How's physics going? Hello? Hello?
What happened?
I said, how's physics going?
Oh, physics. Pretty cool, actually. Yeah.
Going pretty well?
Mm-hmm.
Okay, that's great. So which problems would you like to work on? I have them. Do you see my screen?
Yes.
Okay. So I've got all of the problems right here in the corner. So just let me know maybe which one you'd like to look at or start with, and I'd be happy to go from there.
Well, we can start from the beginning. Number 28.
Sounds.
Yeah.
So this one, let me see if I can just. Guess I can't make it any smaller than that. Wish I could make it a little smaller. No, it won't let me. That's okay. All right. So, ooh. All right. So, circular motion is the unit that you're in right now. You're in a unit. The name of the unit you're in is circular motion, and that's what we had spoken about in our last session.
Yeah.
And in that unit, it does include a lot of stuff related to planets, as you might have seen in terms of the surface gravity on a planet. Some things involving orbital motion, which is when a planet orbits in a circular circular shape around something like a star, and so that's all tied into the same unit, and it involves two main subtopics. One is Newton's law for universal gravitation, and that's just his law that he developed to be able to determine how much force one planet might be pulling on another planet with, like our Earth pulls on the moon and the moon pulls back on the Earth.
Yeah.
And so the so-called universal law of gravitation would be a way of determining how much force each of those planets feel, recognizing they'd actually be equal because of Newton's third law. Anytime something in the universe, no matter what it is, if it's two people or two planets, if one of those objects pulls on the other object, they both feel the exact quantity of force, and people would typically say the magnitude is equal. The magnitude of the force they feel is equal, but they feel them in opposite directions. So the Earth would pulls on the moon with a certain amount of force, pulls the moon towards us, Earth, and then the moon pulls on the Earth with an equal amount of force, pulls the Earth towards the moon. I'm just pointing that out, but they're always equal forces, and Newton's law of universal gravity would allow you to calculate what that amount of force is. And so that's one of the subtopics here. And included in that is determining how much gravity might be on the surface of a planet. And for us on Earth, that number is the number 9.8. So, yeah, and that's in reference to how much gravity there is at a certain distance away from the center of a planet. And it's 9.8, of course, for us, and that's referenced as the gravitational field. So the strength of a gravity field is measured as how much acceleration it produces when you release something next to that planet. So when you held out your pen and released it, its speed would increase by 9.8 meters per second for every second as it fell towards the Earth. And so we call that the strength of the gravitational field of the Earth, because it will accelerate all objects that are released other than feathers and papers and things like that, for the reason that they're light and air affects them a little differently. But if there was no air and no atmosphere like on the moon, it doesn't matter whether you drop a car or you drop a little pebble, they'll both accelerate at exactly the same rate. Even if you drop a feather on the moon, it would accelerate exactly at the same rate as the car, because there'd be no air to affect the motion of the feather. And that's called the strength of the gravity. And for us, on this planet, it's 9.8. Okay, so that being said, that's just like a little recap of the unit. Looking at 28, it says calculate the force of Earth's gravity on a spacecraft 2 Earth radii above the Earth's surface if its mass is 1,850. Okay. So let's start with some starting points here. I'm going to draw a little picture of. Oops, sorry. I'm going to draw a little picture like this. So this is represented as like one curved portion of the Earth. It's not a perfect curve, but I think you get the idea. This is Earth. And this would be considered the radius of the Earth, R.
Okay. Yes.
And going back to, where's my mouse? Going back to here, they're asking you to calculate how much force Earth's gravity would place on a spacecraft at a distance 2 Earth radii above the the surface of the Earth. And so what that means is this line right here can be thought of as 1 radii away from Earth's center. Because this distance is the center of the Earth right here. So at this particular point, along this line right here, that's considered 1 radii away, right? Well, specifically at this particular point here. And so if we made one more of those distances, and then another one, and I'm making them equal on purpose, this distance here would be considered 2r.
Radii.
Yep, 2 radii away. And this one here would be 3 radii away to this point here. And they had said they wanted it to be a point in space 2 radii above. They didn't say 2 radii away from the Earth's center. And let me actually check just to make sure that, because you have to be careful with the wording, the way they word it. Let's look one more time. 2 Earth radii above. You see the word above? Above the Earth's surface. So that's why the point they're interested is out here, because this is 1 radii above, and this is right here above the surface of the Earth. Remember, the surface of the Earth is right along this line, and this is one more, right? Does that make sense? So, okay, this is our point here. So that's the picture. Now the question is, how do we go about formulating an equation based on what Newton had figured out long ago, 400 years ago in the 1600s, at a very early age of, in his young 20s, early 20s, he had figured all this stuff out, including calculus. But interestingly, you can determine a lot of these sorts of problems and get a reasonably good answer without any advanced math, just using algebra and his equations. So I wish I had more space, but I'll try to write it right over here. His universal law for gravity is that the gravitational force is between, and what did they say was here? A spacecraft, right?
Yeah.
So let's say this is our spacecraft. And the spacecraft has some mass, and we're going to call it lowercase m. And then the Earth is, of course, significantly larger, and for that reason, we're going to call it capital M, okay? Just to distinguish them. Capital to indicate it's big, and the lowercase m on the spacecraft just indicate it's a small mass, okay? And so what he determined is that, for one, let's talk about the proportionalities. Something weird happened there. Proportionalities. So what he determined, and actually, it's quite amazing when you realize that you're actually smart enough and anybody, I'm not just trying to pinpoint you, just anybody that has used a reasonably good science mind or better can actually make sense of a lot of these equations because they're built on common sense. I mean, there are some parts of the equations he figured out that wouldn't be common sense, and it really did take a brilliant mind to figure out. But other parts of the equations are actually common sense. And so let me give you an example. If you have 2 magnets, you do agree that you can make them so they pull on each other, right?
Yeah.
And that's what the planets do. You know, Earth and Moon pull on each other. And it turns out that even when you have a spacecraft far, far away floating in outer space, Earth's gravity is still pulling. So that's a misconception that some people have, is that Earth's gravity only exists right here on the surface of the Earth, and as soon as you go into space a little bit, there's no gravity up there. That's actually a misconception. There is gravity, Earth's gravity, and it actually extends all the way out into the infinite universe, forever. But it does, well, without saying this, I'll let you determine what I was about to say. You have two magnets that are like an analogy for this. In which case do they pull on each other the strongest, when they're far apart or when they're close together?
They're close together.
Close together, right? And so building a little picture of that down below, if you have one magnet and a little distance and another magnet, compared to one magnet and a large, distance between them and another magnet, this is considered a large distance. This is considered a small distance, right? And in which case would they pull the greatest force? Choice A or choice B? It would be choice A when they're closer together, right? So that means when the distance between them is small, the force between them is
stronger.
Exactly, strong. I'll just call it big. When but you had the right idea. They're strong. It's a stronger force. So when R is small, F is big. Does that make sense?
Yes.
How about in this case, when you take the two magnets and you separate them by a much larger distance, R is big.
Big, which will make F smaller.
Exactly. Ooh, my pen is. What's happening here? Hold on a second. Something bad happened. Hold on a minute. I'm not sure what happened. There it goes again. Oh, I can't draw over there, I guess. So you got the idea that when R is, well, still won't let me, there it goes. When R is large, I'll just put an up arrow to indicate the thing larger. What happens to the force between them? It drops, right? The magnet's force between them drops and diminishes as the distance gets larger and larger and larger. It turns out that planets are that same way. And that idea that when one gets big, the other gets small, or when one gets small, the other gets big, is that called directly proportional or inversely proportional?
Inversely proportional.
Inversely proportional, exactly. And so when you identify that idea, which he certainly did, he probably played with magnets and he did identify that idea, and he probably logicked out in his mind that planets might be the same way, and he was right, they are. When two planets are close together, they pull on each other with lots of force, just like magnets. When two planets are far apart, they pull on each other with just a little bit of force, just planets again. And so he built an equation to reflect that. So would it make sense for him when he built his equation, which was that the force of gravity between two planets, imagine that there's some sort of ratio, and a lot of physics equations do come out to be some sort of ratio, some things in the numerator and some things in the denominator. Where would you place R, the distance between the planet and the spacecraft in this case? Would you put R in the numerator of this or the denominator?
Denominator.
A denominator, exactly. He had rationalized that as well. Obviously, he was very bright with math also, so that helped him. But that's why he put R down here, because when you have something in the numerator that's on the left side of the equation and something that's in the denominator on the other side of the equation, then they're inversely related. And as one goes up, the other will go down, right? And that can be even shown just with a simple idea of like y equals, 1 over x, right? If x is 1, then y is 1, right? If x is 2, that means the denominator is getting bigger. What happens to y?
It's 2.
It's 1 over 2, which is what?
1 over 2 would be half.
Half, see? So as x increased from 1 to 2, what did y do?
It decreased.
Decreased. Yeah, it decreased from 1.5. And so anything that has that relationship, in this case, y is in the numerator on one side and x is in the denominator on the other side, that's an inverse relationship. One goes up, the other goes down. And so he built his model for this, which has come to be known as the universal law of gravitation that we're working out here on the top left. He built it on that idea.
Okay.
The other thing he realized is that even with magnets, if you had two tiny magnets, they might pull on each other with just a little bit of force. But if he had taken away one of the tiny magnets, left the other tiny magnet, so he starts with two tiny magnets and just observes that there's a little bit of force. Gets rid of one of the tiny magnets and slides in a really large magnet. and then sees how much force does that generate when you have a tiny magnet, and now instead of another tiny magnet, you've got a larger magnet. He's increased the mass of the magnet. What would you expect to happen to the force?
It becomes stronger.
Stronger, right? He logicked that out as well. He probably did. And my guess is he probably did play with magnets to develop some of these ideas.
Thinking that, considering the size of the sun.
Exactly.
To the sun, you still feel the sun's gravitational pull on the Earth.
Exactly, exactly. And so he realized that when he was trying to develop a formula that would be used to determine how much force two planets pull on each other with, he realized distance was one of the important factors, because it's a distance sensitive force. When they're close, they pull strongly. When they're far away, they pull less. And then he also realized that the size of the object mattered. Like two really huge magnets would pull it on each other at some distance apart with a really strong force. And then if you put two really tiny magnets that same distance apart, they wouldn't pull on each other with as much force. So he realized mass was the other important factor in this equation, which is why the sun, like you were saying, generates huge amounts of force, primarily because it has so much mass. It's like a giant magnet compared to a tiny magnet. So where would the m's go in our ratio, on the top or the bottom?
The top.
Exactly, they go on the top for that reason. And he realized that it didn't matter just about one of the object's mass. He realized that both of the, if you're looking at the Earth and the Sun, for example, wondering how much force the Earth and the Sun pull on each other with, he realized both planets' mass mattered. That it wasn't just the mass of the Sun that was going to be in his equation, or just the mass of the Earth. He determined it was actually going to be the product of both of their masses. And they're both going to be in the numerator. So this would be, in our problem, m and then a little m. Remembering that the big M was the mass of the Earth and the little m was the mass of the spacecraft. It doesn't really matter if the little object is just a smaller planet or you just floating in outer space. Even if it was you, you'd be the smaller m there in that equation, and you would still feel a pull from the planet, and it would slowly be accelerating you towards the planet if you were just placed at that point. Does that make sense?
Yes.
And so so that's the part that I think is logical, because you can just use common experience even with magnets to almost work this out so far. However, the part that's not logical is the idea that this is actually squared in the bottom. So this is actually r squared. And the other part that's missing here is, I'd have to erase this, is that there's something called a proportionality constant. Have you learned about those sorts of things before? So a proportionality constant is something in physics that indicates that there is some proportion being held, like the gravity force is proportional to the masses. So that means directly proportional, in fact. So that means if the masses of the planets increase, the force of the gravity would also increase. It's also correct to state that the force of gravity between two planets is inversely proportional to the distance between them squared. And that distance is represented as r. So when there are things that change in an equation, there's always one thing that doesn't change. It stays constant, and it's called a proportionality constant. And that got the letter, do you know what it is in this equation?
Yeah, sure.
Capital G.
For gravity.
Yep, they gave it G, that letter, for gravity. And so let me come over here. It's just a constant number, like pi. It's a number, right?
Yeah.
Does it ever change?
No.
No, just a number. There are a whole bunch of constants in nature. Pi is just one geometrical constant that I can think of right now. But there are tremendous amounts when it comes to magnetism. There's a magnetism constant. When it comes to electricity, there's an electrical constant. When it comes to gravity, there's this gravitational constant. And that's actually what that thing is called. It's called the gravitational constant. Oops, sorry.
Okay.
And it's just a number. So it never really ends up being a very important thing, but just know that it's still used when you're trying to calculate something. And the value is 6.67 times 10 to the minus 11. It's very small. Times 10 to the minus 11 is like 0.000000 with all those zeros. 10 times 667, right? It's almost the value zero, but not quite zero.
Okay.
And that's called the gravity constant. So now, and I know while we're talking about this problem, but I'm really building a much larger structure for you so that you understand the large picture.
Yes, sir.
So the next idea is that Newton's second law, let me actually erase a little more. over here. Do you remember what Newton's second law is?
Off the top of my head.
Okay.
Where is it? I wrote it down.
It's okay. It's the only one that's actually like gets an equation form. Newton's first law is kind of a statement. Newton's third law is more or less a statement as well, and then Newton's second law is the one that's the equation that you use in a lot of the physics.
The F equals ma times A.
Yep, you got it. It's that the net force acting on some object is always equal.
Mass total times equals the acceleration.
Yep.
Mass times acceleration equals force.
Exactly. So if you had a car, like a physical car accelerating on the highway, that car has a certain mass, and if it was accelerating at a constant rate and gaining a certain set amount of speed per second, that's called acceleration of the vehicle, right?
Yeah.
And if you multiplied the mass of the vehicle times the acceleration of the vehicle together, you get this number that represents total net force acting on that vehicle during that time while it's accelerating at that rate.
Okay.
And so that's the idea of Newton's second law. It turns out that when you're talking about gravity and you're talking about an acceleration due to gravity, you take away the A and you call it what letter? For the acceleration due to gravity, we call it 9. The number is 9.8. G, exactly. That's called the acceleration due to gravity. So when you're in a gravity chapter like this, like you're in now, you would write this as F net equals mg. In fact, that's an equation you've used before. Do you recognize it?
Yes.
What do you use that to calculate? Mg.
Friction force?
Good guess. That's actually partially correct. That's mostly correct. But mg represents the weight of an object in newtons.
Oh, yeah.
You remember that now?
Yeah.
Okay, perfect. Turns out that essentially what Isaac Newton did is he determined there was two equations that both kind of can be used to calculate the same thing. One of them I just put a box around, and the other was the other one right here. Because what actually this is called weight. What actually provides us with a sense of weight? The force of gravity does. If we don't have any gravity in our environment, or we're not near a planet, we're weightless. We're not massless. We still have a certain mass. So if we're floating in outer space, someone wants to get us moving, they do still have to overcome our inertia and push on us a bit to get us to accelerate. But if we were floating in outer space, we wouldn't be pulled towards the surface of a planet. We would have no bathroom scale to place, down. We wouldn't have a planet to place a bathroom scale down on, and we would literally have no weight. So it's a very important idea that recognizing, because we're going to have to merge those two ideas and these two equations together, that the gravity force is called your weight, right? And so do we have an equation over here for the gravity force? Yes, we do. And do we have an equation over here for weight?
Yes.
Oops. Yes, we do. And the gravity force is your weight. It's this one and the same thing. And so we can set those equal to each other. See that? Turns out, this is a fascinating thing. When I actually learned physics for the first time, this was one of those moments where I was like, wow, that's pretty amazing. And give me 1 minute to explain this. In the equation on the left, if you wanted to calculate how much gravity force the Earth is pulling on your physical body right now in the downward direction, what is that quantity known as? Your weight. What do we measure it in America? In pounds. Yep, on a bathroom scale. Could that be converted into a force measured in newtons? We could. Yep. What equation would we use to calculate what that bathroom scale would read in newtons? The one right there on the top left. How would we use it? We need to use this really tiny number on the top right of the page, 6.67 times 10 to the minus 11. That goes into the equation for G. We would need to go online and Google whatever the mass of the Earth is, put that in for capital M. We put your physical mass. I'm about 90 kilograms. If it was for me, I'd put the number 90 in for little m. And then how far am I away from the center of the Earth? Well, I'm on the surface of the Earth, so the distance between me and the center of the Earth is just the radius of the Earth, right?
Yeah.
I'd go online and Google that, find it as a number in meters, put it in that denominator, punch all those numbers into a calculator. I get around the number 900 newtons. So my weight in American units, pounds, is about 200 pounds. But if I was other places in the world who do measure things in newtons, the bathroom scale would read 900 newtons. It measures exactly how much gravity force is pulling me down. So my weight in newtons is the number 900. Amazingly, if you come over to this equation on the right, over here, and plug in, since I know G is 9.8, right?
Yeah.
So if I actually came over and said, I wonder what this equation would give me for my weight, because it's supposed to be an equation for weight. And if I plugged in my same mass of about 90 kilograms there and multiplied it by G, 9.8, guess what number I'll get?
You get
900. I'll get the same number that this other more complicated equation on the left produces. You see that?
Yeah.
Yeah, that's a pretty amazing thing. And what it's telling you is that you can calculate how much force exists between two objects, even if you don't know what G is. If you're on a planet, that weight is related to the strength of the gravity on that planet, and it's G. If you don't know what G is on that planet, you can still use the equation on the left, because notice there's no little g over there. There's a capital G. Recognize capital G and lowercase g are two different things. Capital gravity constant is that tiny number on the top right of the screen. Lowercase g is the acceleration due to gravity on a certain planet. For us, it's the number 9.8. Right?
Oh, yes.
And so the point is, if you don't know G, you can still calculate the force between two objects in the universe, as long as you know how far apart they are, capital R, and their masses. You multiply them in and you put them all in the equation, you're good to go. On the other hand, if you know what G is, like we do know what G is on the surface of our planet, the number 9.8, you can also just make it much easier for yourself and plug mass of U and G, and you get the same number. The point is, we have to understand this to solve this problem. Since those actually are the same equation, just presented differently, we can set them equal to each other. So, in fact, let me go over here. I didn't mean to draw F. So do you understand the point of what I'm making, that they provide the same numerical value?
Yes.
So they're really like the same equation. They're not the same equation. They're different equations, but they produce the same thing. So we can set them equal to each other. And so coming back, I can now write capital G times the mass of whatever this giant object is, might be the Earth, times the mass, the little m is the mass of the spacecraft that's still floating out here, right? Divided by, I'm just going to call it R for now, and we'll figure out the 3R, the 2R that was in the problem. We'll figure that part out later. So I'm just going to call R the distance between. So I'm going to just call the distance from the center of the Earth all the way out to the spacecraft. I'm just going to call that R for right now. Is that all right? Hello? 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 Okay, sorry. Hello?
Yeah.
Okay. So all I was pointing out is that the distance between the center of the Earth and the spacecraft is called little r right now. I'm just going to, and I'll give the other part of it 3R or 2R later. Okay? And also it's important to recognize, and this isn't obvious, when people are talking about calculating the force between two planets, most people might be inclined to measure the distance from the surface of one planet to the surface of the other planet and consider that the distance between them. And actually that's not right. It's the distance from the center of one planet to the center of the other planet. It has to include the radius of each of the planets.
Okay.
Okay? And that's why when I just drew that in, my line had to start right here, right at the center of the planet, and all the way over to the center of the spacecraft.
Okay.
Okay, and so all I'm doing is setting these two equations equal. I'm going to put my squared in, and I'm going to put that equal to mg. Notice what happens to the little m, the mass of the space. It cancels out. That's a really important idea, that cancels out. It means that you are actually able to generate an equation now. Trying to figure out where I'm going to continue writing. Give me a second. It means that you're able to generate an equation that provides you with how strong Earth's gravity is. Do you see how there's the G is still in there? The little lowercase g, I should say. Lowercase g is the strength of Earth's gravity, and you want to know how strong is it on planet Earth? I mean, on the surface of Earth, the number 9.8. But if you went out further into space, that number 9.8 would start dropping. You know, a couple hundred miles up, it's only maybe the number 9.6. Then if you go a few thousand miles away, it's the number 9.1. And that number that we consider 9.8 diminishes because it reflects how strong gravity is. And if you're going further and further away from the planet, there's less gravity, so that number has to drop. How can you calculate that number? There's that beautiful formula. We just so-called derived that formula. Capital G times the mass of the Earth divided by r squared, and r is now, I'm going to have to erase again. R is just a distance from the center of the Earth to wherever you're trying to figure out how strong gravity is.
Yeah.
So coming back, I'm just going to draw you one more picture. If you had, because my other picture is getting kind of filled up. Why is my pen not working? Here we go. So if this is the curve of the Earth, and you're out here floating in space, this is now just called R. And that R is right here. So that means you might be interested. What is the value for G? You know, at some point in space, as long as you know how far away that point in space is from the center of the Earth, you would plug that value in right here, like I just pointed out, in meters, and then put the value for G, which is that 6.67 times 10 to the minus 11 I mentioned before, would go there, and the mass of the Earth would go right here, and the number would pop out of that equation. Interestingly, if we put the radius of the Earth, guess what number we'll get when we put the radius of the Earth? Because how far away are we right now? In my picture, we're right here, right at the surface. Yeah. And so how far away are we from the center of the Earth? Well, that distance is just the radius of the Earth, right?
Yeah.
So if you plug the radius of the Earth in right here, mass of the Earth right here, G right here, guess what number is going to pop out of this equation? That should be the value for what gravity is here on the surface of the Earth. Guess what number pops out? 9.8 pops out of that equation, sure enough. And when we do experiments to find out what it is, it's exactly that number, 9.8. It's proof that his equation is perfectly correct. Now we can finally build on this, and now we can finally answer your question, because without understanding that, you couldn't really move forward. You couldn't do this. So let's now focus on the problem. So, is there any questions about what I just talked about, or how to get that? Because once you see it and then you see how to use it, you realize the math part of it is actually quite easy. There's not a lot of complicated math with it, but understanding the concepts that I kind of reviewed with you are pretty important when it comes to the AP exam, at least. But in terms of some of the math, it's not that difficult. You'll find it's pretty easy. Okay, so are there any questions?
No. All
right. So the question, if I can bring it back up now. The question was, and I don't remember exactly what it was. It was, 2 Earth radii away from the surface of the Earth, you've got a spacecraft floating in outer space at that distance. Tells us a mass is 1,850 kilograms of the spacecraft. So the mass of the craft is 1,850 kg. So the point is, can we determine how strong gravity is at that distance, G?
Yes.
Because according to Newton, F equals ma, right, in general? So if we can figure out what the value is for G, the acceleration due to gravity, using this formula, and we can find out what the value for Earth's gravity is out at that distance where the spacecraft is, then we'll have this value right here. We'll have G. If we multiply that by the mass of, because that's where the spacecraft is floating. Like, where are you floating right now? On the surface of the Earth. What's the value of G here? 9.8. We're now interested in what is the force, and again, back to you. If you multiplied your mass times the value of G here, where we're sitting right now, G, you get the force acting on you, known as your weight, right?
Yes.
Can we do that for the spacecraft?
Yes.
Yes, we can. As long as we can calculate what G is for the spacecraft way out there. It's not the number 9.8, because that's only on the surface of the Earth. But when we can calculate it using this equation over here, and we'll be able to do that, all we'll have to do is similarly multiply it by the mass of the spacecraft. And what should that provide? The force of gravity that's pulling on the spacecraft. Does that make sense?
Yes.
So let's do it. In fact, do you want to give it a try now? Do you want to try to calculate G using this?
Yeah.
I can look up these values for you if you want, just to save you some time. You're going to need to know the mass of the Earth, which I have certainly not memorized it. I think it's something around 10 to the 25th or something like that, kilograms. But What's your mass of Earth? 24th. So 5.97 times 10 to the 24th. Oh, what happened to my... There we go. So I'll write that down. Can I erase this picture here in the middle? And I'll draw it again if I have to. If I have to. It's just taking up too much space. All right, that's all there. So the mass of, I'm going to put just E for Earth, is 5.97 times 10 raised to the 24th kilograms. It's a lot.
I just put 5.97. Is it at 6.67?
Okay, that's actually G. The gravitation constant.
That's
Yeah.
mass of the Earth. Oh,
No problem.
I thought you put that for G.
No problem. So you actually do need both of those. And then I'll write the distance down, which is just the radius of the Earth.
Is it 10 to 29?
Yeah, I'm sorry, that's kind of messy. That's actually 10 to the 24th.
The 24th. Oh.
Yeah. And the radius of the Earth is about 4,000 miles, but can we use miles? No, it's got to be in meters. So, let's see, radius. Oh, there it is, right there. No, is it giving it? Not giving it to me in meters. Still giving it to me in miles. I don't want it in miles. All right. Well, that doesn't really matter. Well, the number there does matter. 3959. Why did I? There we go. I'll just write that down. You won't be able to use it. 3959 miles. And I do know that there's 1,610 meters in 1 mile. So maybe you could work out that distance in miles. There's 1,610 meters per 1 mile, and the radius of the Earth is almost 4,000 miles. So you'd have to work out that distance just to try to convert the radius of the Earth into meters. But remember, that's not the R that's going to go into your equation, because how many R's away is it?
3R.
3R. Good job. You remembered the image that I drew for you. Yep. So what you have to do is just work out what R1 radius, Earth radius is in meters, and then you'll have to multiply that by 3, and that number would...
The radius in meters is about 637. 6,337,398.
Correct. What would you write that as in scientific notation? Round to 2 decimals if you want.
2 decimals, okay. I get 6.4.
So that would be rounding to 2 digits, but you need to round to 2 decimals.
36.37.
Very good.
Times 10 to 6.
Yep, you got it. Meters. And how many radius is that? That's just 1, remember?
Mm-hmm.
So that's just the radius of our Earth, the radius of our planet Earth in meters. But you already told me that spacecraft is 3 times further away than that, right? Yep. So what do you have to do to that number?
I have to multiply that by 3.
Yep. So I'll do the same thing on mine just to confirm what you're getting. And when you're in this planetary stuff, a lot of the numbers you're dealing with are big. So you definitely want to be using scientific notation, and typically rounding to 2 decimals is more than sufficient. Hello?
Yeah.
Okay, you're still working on it.
Yeah.
Don't rush.
Thank you.
But what I'm going to do is I'm going to just erase this part here. Don't really need that anymore. Don't really need any of that anymore. And I'm going to start writing it in for you. Just so it's...
1.91 times 10 to the 7.
So let me give it a quick try on here also. Yeah. That's correct.
Okay.
Well, that's the distance from the center of the Earth to the spacecraft.
Mm-hmm.
Yep, that's right. And so now we need to plug all of those values into that main formula on the bottom left of the screen. Right?
Mm-hmm.
So you're going to use the gravity constant, which is 6.67 times 10 to the minus 11, in parentheses, assuming you have a graphing calculator.
Yeah,
Some sort of scientific, okay. And then the mass of the Earth, I have to go in as well.
Would I square the 1.917?
Yeah, so can I make a point? Some of my students try putting all of these things into their calculator all at once and hitting enter, and a lot of them make mistakes because they don't enter it in correctly. So I'm going to make a recommendation, but I'll let you make your own choice. For me, even to this day, and I've been doing physics for a long time, I still do it this way because it worked when I was 20 and it still works for me. And I know I can count on it and I don't have to worry about making mistakes because your calculator, if you put a parenthesis in the wrong spot or missing one, you know that your calculator thinks you're asking something else and it gives you a number that's wrong. It gives you an answer that's wrong because it thinks you're asking for some other kind of operation. So what I recommend doing is always working out the denominator first. So what is our denominator? It's the distance that you had just told me, right? 1.91.
Yeah,
so I would put that number into your calculator by itself right now and square it, since it's r squared. And then I'll teach you a little trick after you do that.
Okay, so I'm gonna go grab something real quick.
Okay.
I got 8.56, 8.5, 8.65 times 10 to the
So you must not be on you must not be in scientific mode. So hit mode. Do you see the button mode? The button that's labeled mode is next to the top left.
Okay, I see it.
On the very top, where's that blinking box? Does it say normal, science, or engineering?
I see it.
What does it say?
Yes, normal science, engineering.
Which block? Where is your block? Where's the black box?
It was on normal. I just switched it to
Okay. Because it should provide you with your answer and say e to the 14th, which tells you that's times 10 to the 14th.
Yeah, that's right.
Okay. Can I point out one other thing, just to give you a sense? Because a lot of my students do this sort of thing, and they never just think about some of the math skills they learned previously. They just rely on their calculator, and they never second guess it. Can I point out that what is the number 1.91 pretty close to? What number is 1.91 really close? What number?
2.
2. So is this kind of like 2 times 10 to the 7th? Well, yeah, it kind of is, approximately. And if we were squaring that, would you have to square the first number here as well as this number here? Turns out, yes, that's a math rule that you have to distribute that square. So what is 2 times 2? 4. What is 10 to the 7th squared?
10 to the 7th.
What's the rule for how you handle these exponents?
Next better.
Yep. So it gives us times 10 to the what?
Times 10 to the 14th.
Right. What number did you get on your calculator?
3.65.
Times 10 to the
14.
Do you see that?
Shortcuts.
Does that make sense to you?
Yeah.
Okay. I just wanted to make sure you see that. So that's why sometimes you can have a working knowledge so that when you're looking at either a computer program or like a calculator, you can start second guessing what that answer is. Because you can sometimes get a feel for what your answer will be, and you'll be able to tell right away that something's not right. I must have hit the wrong key. All right, so moving on. Now, let me just erase that. How are you going to move on from here?
Now I'm just going to multiply the two numerators.
Yep. Oh, wait, let me teach you this trick now. So do you still have that number in your calculator just sitting there?
3.6.
Yep, times 10 to the 14th.
Yeah.
So now, this is a really cool trick, so really pay attention here. Down on the bottom left, see how it says on? Your on button on the bottom left of your graphing calculator?
Yeah.
One button above it, see how it says STO?
Yeah.
Press that button. And it says answer, ASS, ANS, and then arrow. That means I'm going to store the previous answer, which is the one that you want to store for a minute. Store it as X, and the X is in mode, right under the mode button. So hit store.
Repeat the run back to me again.
Yep. So hit the button that's right above the on button. It says STO.
STO.
And does it say now, did something come onto your screen when you hit that?
Yeah, answer, and then.
Yeah, it means you're asking the calculator to store the previous answer, the 3.64 times 10 to the 14th number, so you don't have to write it down anywhere. You're going to store that as the symbol X. And press the letter X, which is next to the mode button, next to where it says second, the yellow second button. See how it says, that's where your X button is, the X symbol?
Oh, for like alpha and then X?
Yep, store it at X, and that X is right under the mode button. You see it? And then hit enter. And it repeats it back to you again. You see that?
Yeah.
Now hit 2 times X, enter, just to show you an idea.
It gives me 7.3.
Is that 2 times that number?
Yes, it is.
It is. You see, so that's a way of storing a number so that you can use it later. So the point is you've worked out what the denominator is squared, and rather than writing it down, and I have students that write it down with 9 decimals, 9.655, write it all down, and they go back in, they're typing it all in, and this is a little shortcut because now it stores that. And you don't even, right, and at the very end, you'll hit divide by X, and you'll be done. You see my point?
Yeah.
So now work on your numerator. And this is what I was explaining. Worked for me when I was 20 years old, and it still works for me 20 years later. And I still rely on it, and it does not ever go to fail me. Some students insist that they're going to put all of it in at once. And I tell them, it's tough. If you do make a little mistake with the parentheses, it's going to give you a bad answer. And they eventually agree with me by the end of the year, yeah, it is best to just go one little piece at a time. So work on your numerator now. It's capital G, which represents this gravitational constant. It's called the universal gravitational constant. It's that really tiny number, 6.67 times 10 to the minus 11. And that, just as a little insight, which you wouldn't get from your book, you might get it from your book. It's really that tiny number because gravity force is the weakest force in nature. Magnetism is much stronger than gravity. Electricity is much stronger than gravity. And that proportionality constant, called capital G, is such a tiny number, 0.00000000667, to reflect the idea that gravity in our universe is actually quite weak. When you look at the electricity constants, numbers that are much bigger to reflect the idea that electricity is a much stronger force in nature. And you look at the magnetism constant, much larger number to reflect the idea that magnetism is a much stronger force in nature. So that's just a little insight, but not important right now.
Can I split the number that I got for the numerator too, and then just put like...
So yeah, just plug in 6.67 times 10 to the minus 11.
I got 3.98 things.
Yeah, and now you don't even have to store that. Now, once you get the answer to the numerator, just hit divide by x.
Divide by x.
Does that make sense?
Yeah.
And that's it. And
I get 1.09.
So I'm going to do it myself. I haven't done it yet. 1 second. 11 times the mass of the Earth, which was what, 5.97 times 10 to the 24th. Enter. So I got my numerator, and then I just hit divide by x. 1.09 times, just 1.09.
Yeah, it's 1.09.
That's great, right? Because if it was a huge number, would that be a problem? Let's say it was the number 1,000. Would you say, that can't be right?
Mm-hmm.
Why would you say that can't be right? How would you justify that?
Because they were both huge numbers. If they would be divided by themselves, but like, it wouldn't make sense.
Right? Let me show you another idea, though. This is when physics starts to really become such a beautiful thing to me. At the surface of the Earth, the value for G is 9.8 along all points along the surface of the Earth. No matter where you are, it's 9.8. Because at any point, how far are you away from the center? A distance r, and those are all equal distances. You see what I'm drawing?
Yeah.
Right?
Yes.
However, let's say you decided to float out here in outer space. Could this possibly be the number 1,000 meters per second squared at this point in space? Is that a reasonable number? Let's say you just got that for your answer. Would you have to question the computer and say, that's not right? Or
yeah.
And why? Why can't that be?
Because that's too far.
What happens to gravity as you go far away? Gets less. So does our answer have to be a number less than 9.8?
Yes.
Yes. Is it?
Yes.
Yes. It's the number 1.06. Does that agree with logic?
Right.
You see how that agrees with logic?
Yeah.
It has to be less. So in the real world, out here, it might be the number 9.6. A little further away, G might be 9.4. Way out here, it might be the number 5.2. You've come out so far that the value for the strength of Earth's gravity is the number 1.06. You see? And it couldn't have been a number greater than 9.8 because that means you made a mistake, because that's not how the universe works. When you get further and further away from a planet, gravity drops. Its maximum value, the Earth's gravity, is strongest at the surface of the Earth. And any distance further away from the surface, it's always a value less than 9.8. So now you can finally finish the problem. Let's come back to it, and I know it's a lot of steps, but that's how physics is. That's why it's such a hard subject, and you are blessed to be somebody that can ponder these sorts of beautiful ideas and work them out, because most people say, forget that. This stuff is too complicated. But my point is, let's come back to the problem. It was a lot of steps, but let's go back. I can make this work. Lost all that. Back to the problem. Do you now know what G is at that distance 2 Earth radii above the surface of the Earth? You do. What number is it?
1.09.
1.09 meters per second squared. That means if you released a penny at that point, just went like Superman, fly over there and drop the penny, would it start to accelerate?
Yeah.
Yes. In which direction would it start moving?
Downward towards the center of the Earth.
Straight towards the Earth. 1 second later, what would its speed be, based on your answer?
1.09.
Yep, about 1 meter per second would it be its speed if it had a speedometer attached to it. 2 seconds later, what would the speedometer read? About what number?
1.9.
About 2 meters per second, right?
Yeah.
3 seconds later, what would its speed be?
3
meters per second. Would it be accelerating?
Yeah.
Yeah, it's gaining 1 meter per second of speed as it starts accelerating in the direction of the Earth, continually gaining 1 meter per second of speed for every second. And so with all that now locked away, the question is, what is the total force acting on the satellite? You know what acceleration it experiences. What do we have to do to finish the problem off?
So the equation that we need is mass net
Equals what?
equals mass times g.
Yep. Do you have G?
You just need to plug in mass.
You just need to multiply by the mass of the satellite.
The mass of the satellite was
1,850 kilograms.
yeah, 1,850 kilograms. So it's just going to be 1,850
Times.
1.09.
You got it. Should be close to 1850, but a little higher.
50. Yeah, it's probably right. Like, so F n equals. I got 2.02.
Yep.
10 to the third.
Yep. Which is to the 10 to the third is 10 times 10 times 10, which is 1,000. 10 times 10 is 100, times another 10 is 1,000, times 2 is about 2,000. And that makes sense, because it was the number 1850 times a number that was slightly greater than 1.06. Should be a number slightly greater than 1850, which is about 2,000, or whatever you have, it's right. And what would the unit for that be? And what does it represent, just so I make sure you're not just focused on numbers, you're understanding ideas. What does that number represent?
The force, 10.
That who feels?
That the spaceship feels.
Correct. And this is where the AP exam would ask a conceptual question. I know we're doing a lot of work for computation. Would you agree?
Yeah.
And I'm reminding you, you're probably not going to use your calculator at all on the AP exam.
Okay.
But you want to go do mechanical engineering, if I remember, or no,
Mechanical engineering, yeah.
Right. So just promise. I mean, I promise you. I have a degree in physics, and I guarantee, in your very freshman year of college, are you going to be doing a lot of concept questions and a lot of writing? No. I mean, you'll have some concept questions. You'll have almost no writing. What will you mostly be doing? Calculations.
Okay.
It'll be very heavy in math. So this is very much preparing you for that stage of your life. That's the direction you go in. However, for the AP exam in high school, they've said, you know what, let's let them deal with a lot of the calculations when they get to college. Let's teach them some of the concepts, because when they get to college, a lot of professors like to just stand there and do math on the board. And they don't actually, to be honest, even in my own experience with a degree in physics, they didn't teach me a lot of the concepts I needed. I had to learn them on my own. They just stood there and do math. And you learn how to do all the calculations, but you come away with not as much conceptual understanding as to what's really going on. And so the whole idea is now that you learn a lot of that concept now in high school, you go to college if that's the direction you want to go in, and you learn a lot of the computation. So that being said, your professor is giving you just all math problems. And that's good. That is good for the reason I just described. But just remember, the AP exam is almost all concept. Yes. And so my point and question that I'll try to mimic what kind of questions they would ask. They'd say, okay, as that object's accelerating towards the planet Earth, the spacecraft that's far, far away, 3R away from the center of the Earth, starts accelerating towards the center of the Earth. What happens to the acceleration? And that's called the instantaneous acceleration. Instantaneous acceleration is what the acceleration is at any given moment. So as it starts sliding or moving towards the Earth, let's say a minute later, it will be a lot closer, right? Will the acceleration it experiences at that moment in time, called the instantaneous acceleration at that moment in time, still be the number 1.06? And then they would say, actually they would frame it in this way. Will the acceleration it feels 5 minutes later be greater than 1.06, still 1.06, or less than 1.06, and why? And then you'd have to choose. You'd normally circle your answer, greater, less than, or same. And then they'd say, now here's 5 or 6, 7 lines of space. Go ahead and just justify your reasoning, and you'd write. You want to take a crack at that one?
Yeah, it would be greater than 1.06. Since the acceleration closer, it's accelerating closer to the center of the Earth, the force of gravity, the pole is becoming stronger and stronger as it approaches the Earth.
Correct.
So
can you keep going?
The acceleration would be greater than 1.06.
Perfectly nicely said. So you did point out that it's closer, and They want to hear the because statements, because if you want to get really good scores when these people that are hired to score all these AP exams, they're using rubrics, they're looking for because statements, and they're looking for really solid because statements. So you stated it will be closer, and it will experience larger force from the Earth, gravity force, when it's closer, but what was the because of that? Because why? Why will it experience greater force when it gets closer to the Earth?
Because the two masses, the force of gravity is not what I'm looking for.
Because the force of gravity between two objects does what when they get closer? Increases, decreases?
It increases as the objects become closer. Perfect.
That would get the full points. And if the force of gravity is increasing because they're closer, how does that affect acceleration if the force goes up?
Acceleration also increase.
And therefore, it would be a number larger than 1.806, still 1.06, or less than 1.06. Greater than 1.06. Correct. Yep. Yep. Very good. Good job on that.
Thank you.
Yeah. And lastly, let me come back to, where's my screen? One more quick comment. They also give graph questions, and I might as well throw it at you and see what you think. This is, I know I've been doing the AP for about 10 years, and I know I've come to know them very well. I know what their exams are like, what kind of questions. So they would do something like this. They say, which one of these graphs best reflects the force of gravity that the spacecraft experiences while it moves in the direction of the Earth? Because we agreed that if you just kind of plopped the spacecraft, I know we don't plop them there, but just imagine all of a sudden you just threw it there. All of a sudden the spacecraft appears at that point. It starts sliding towards the Earth, accelerating towards the Earth, and they would say, what would that force if we had some force sensor on the spacecraft, and that force sensor could tell us how much gravity force it feels from planet Earth as a function of, meaning depending on the distance between the center of the Earth out to that spacecraft, and we're going to call that distance r, what would that graph look like? They would give you 4 choices, A, B, C, and D, and each of them will look a little different. Without me writing 4 of them, could you make a guess as to what the shape of the graph would look like? Indicating how much force how much gravity force the spacecraft experiences as r is going to get what, larger or smaller, or stay the same while it moves towards the Earth?
The graph will up.
Will the distance between the spacecraft and the Earth get smaller, larger, or stay the same while the spacecraft moves towards the Earth? The distance between the Earth and the spacecraft.
Oh, it'll decrease.
It'll decrease. So as r decreases, what will the force do?
It will increase.
So could you try to take a guess at what that sketch would look like? I wish we could share a whiteboard. That would be pretty awesome. I wonder if we could talk to Barney about that. Is there a way of us sharing a whiteboard so you could write in that right now? Obviously not on my computer. I wonder if that's possible. I'll talk to Barney about that. That would be pretty great. But anyways, could you just describe to me in words? I guess that's not very efficient, so I will give you 4 choices. But if we could share it.
Maybe have FG on the y-axis and R on the, no. Would it be A?
So hold on, let me give you 4 choices because the AP exam will do exactly that. It's always A through D. And remember, you get 50 problems, and they're not easy problems. So I'm not trying to discourage you. I just want you to know it's a hard test. You got to really work hard on it, and I want you to because you're a smart kid and you have a lot of.
Did you say it's harder than the SAT?
No, I said oh, would I say it's harder? Yeah, it's way harder than the SAT. Significantly harder than. Well, it's different than the SAT. The SAT covers more topics. The AP exam covers less topics, and the problems are harder. Where the SAT covers more topics, but the problems are easier. So they're both pretty challenging. But in terms of if you picked one problem out of the SAT and compared it to one problem from the AP exam, the AP exam problem will definitely be harder. So let me just give you this last choice. They would do like this, they go like this, and then they go like this, And then they go like, what else would they do? This. And then they would go like that. And they'd say, which one of those graphs would be expected to reflect the ideas that you just said, which is that as it gets closer and accelerates in the direction of the Earth, which one of those graphs would reflect the proper relationship between the force of gravity that that spacecraft experiences and the distance, capital R, which represents the distance between the center of the Earth and the spacecraft. Which one?
Would be B.
B. Why do you say B? It's a good choice.
Because let me just like put in a number. Say like where the end of the arrow in between the resultant, right?
Yep.
Say it started at 5, right?
Mm-hmm.
For force.
Right.
The radius would only be 5 would be like a great amount of force, but the radius would only be around 1.
Right.
That would show that as force is greater, the radius is less.
And you might get partial credit for that, to be honest with you. Your choice for B is wrong, but your description was right. And you might, if that was a scoring rubric on the AP exam, you might actually have received partial credit because your justification was correct. So let me explain why. Is this an increasing choice A, is that an increasing function or a decreasing function?
Increasing.
That indicates as the distance R between the two planets gets bigger and bigger and bigger, what's going to happen to the force between them?
And get bigger and bigger.
Bigger and bigger. Is that what we find in our universe?
No.
No. So you know right away that's not right.
Mm-hmm.
Let's look at choice D. Is that an increasing function or a decreasing function?
Kind of an increasing incline.
Yep, that's an increasing function indicating the same thing that we just talked about, which with greater and greater distances between the planets, they'll pull on each other with more force. Is that right? Nope, that's not right for the same reason that A wasn't right. How about this? Is this a decreasing function?
Yes.
Yes. Is this a decreasing function?
Yes.
Yes. They're both. So you had to pick a decreasing function, so you did do that. It happens to be that this is the appropriate decreasing function right here, but your justification probably would have scored partial credit because you justified the fact that it had to be a decreasing function because as the distance between the planets gets larger and larger and larger, it means you're sliding to this way on the graph. What's happening to the value on the y-axis? It's getting smaller and smaller and smaller as you take these data points down like this, right?
Mm-hmm.
So for that reason, you were mostly correct, but it ends up being this one here. And let me point out one last thing. Can you go into your, because we're almost out of time, just a couple minutes. Can you go into your y equals button on your graphing calculator? Can you press that on the very top left?
Yeah.
Can you type in parenthesis, open parenthesis, 1/x, end parentheses? So you're just graphing the function y equals 1 over x. In fact, can you graph it as 1 over x squared instead of 1 over x? It's okay. This will be the last solid point I make, and I hope it sticks with you because it's a pretty important idea. Yep, and just put in, it'll say y1 equals, all by itself it says that, and then you just put parentheses 1/x squared, close parentheses, and then hit the graph button.
Okay, open parentheses what?
So kind of like the way I wrote it, right? If you look, it's
down.
okay. It's okay that you didn't see it right here. If you could write it, type it in just like that, and hit graph. What kind of shape are you going to see? You're going to make the connection. I know you will, and that's the beauty of physics. You learn a lot of math stuff in math class. You learn a lot of physics. As soon as people start allowing you to connect those, you say, wow, this is why we learn the math. So you can apply it and see how they relate to each other, interconnect to each other. It's a beautiful thing, the way that math class. And
it curves down.
Doesn't it do this right here?
Yeah.
Yes. Why is that the same?
Hmm?
So why is it the same as your correct choice should have been choice C? And this is a physics problem. And then I said, go to your graphing calculator and just type in 1 over x squared, and you got the same shape. Why do you think that is?
Because of the proportion.
Correct. The force of gravity, this is the last point I'm making. Can you see my big arrow I just drew in pointing over here?
Yes.
The force of gravity is on this side, that's like y, right? Equals, you have some constant stuff, capital G, M, and M. Do those things change as the position of the space satellite changes? Well, capital G is a constant in nature, it never changes, like pi never changes. As the satellite flies towards the Earth, does the mass of the Earth change?
No.
No, that's the capital M. Does the spacecraft change its mass as it slides and accelerates towards the Earth?
No.
No. So does everything in the numerator change, or does it stay the same?
It stays the same.
Is that like the number 1? The number 1 is just a fixed number, right?
Yes.
And then in math class, we say, well, when we change x, we expect y to change. Similarly, in that equation, r in the denominator changes, and therefore the force of gravity changes, right? And so the point is, r squared, and this is like 1, it's not really 1, it's some crazy number that you had to work out on your calculator, g times m times n. But do you see how these are kind of the same? F equals 1 over r squared and y equals 1 over x squared?
Yeah.
And it forces that shape. And let me lastly point out, you can take that shape in this picture here in both directions. If you increase r, you're separating the two objects further and further. What happens to F, the force of gravity between those two objects? As r increases, what happens to the force of gravity?
It increases.
It decreases. Can you also take those data points the other way and go up this little slide? Yeah, you could. If you're heading in this direction, what's happening to r? It's increasing or decreasing? If you're sliding those data points this way.
Decreasing.
R would be decreasing. That's like the spacecraft moving towards the Earth, right? R is decreasing. What happens to the force of gravity value on that graph as r gets less, less, less?
As the r gets, say that again?
As you take these data points, like this one, this one, this one, and this one, what happened to r? It got less. It's moving to the left, right? What happens to the value on the y-axis?
It would increase.
It goes up, right? Is that a match with what we see? As the spacecraft gets closer to the Earth, r goes down, but what happens to the force of gravity between them?
It increases.
It goes up, right? You see that point?
Yes.
So play that curve in both directions. You can use it as a model to show that as the spacecraft were going further away, and is that important in NASA and stuff? It is, because they might want to take a spacecraft and shoot it over to Mars. What happens to the force of gravity from Earth? Because as that spacecraft is traveling towards Mars, is gravity from the Earth still pulling on it? It is, right? And the force of gravity from Earth extends into all of space. And as r gets larger and larger and larger, because the planet is moving towards Earth, I didn't mean the planet is moving towards Earth, sorry, because the spacecraft is moving towards Mars, going closer and closer to Mars, r is getting bigger and bigger. What happens to the force that spacecraft feels from Earth?
It would be weaker.
It would get weaker, exactly. And that's what this curve is showing. On the other hand, if the spacecraft was all of a sudden flying towards Earth, which your problem was modeled after, r is getting less, 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 what's happening to the force from Earth that the spacecraft feels? Gets stronger. Yep, and that curve shows both of those directions. You see that idea?
Yes.
Yeah. All right, good job. Very good job. I know, again, we only got through one problem, but the point...
It was very helpful. Thank you very much.
Oh, you're very welcome.
I'll probably be able to do the rest.
All right, no problem. Before you leave, let me just point out one last thing. I'm not necessarily talking more about this. I just want to look at your problem set one second. So that one's a little bit challenging. It's why it takes so long to teach. As a teacher, like teaching forces, it could take me a month and a half to teach all the... Huh? It takes me 6 weeks to teach the forces unit.
What happened?
I'm just pointing out, like, a lot of these questions are different, and it just takes so much time to teach it. If you really want to teach it in detail the way I teach you, it takes me 6 weeks to teach the forces unit. And they see me every single day for an hour, It takes a long time. Anyways, 30 you probably have a shot at. It's kind of related, but look at this one, number 32. Do you remember that equation? I hope you wrote that down. G, lowercase g, is the acceleration due to gravity on the surface of a planet. Do you remember me talking about that?
Yeah.
There was an equation for it. If you want to know what the acceleration due to gravity on the surface of a planet is, all you need, let me come back, let me make sure you have this, because you end this, end this lesson. And, yeah.
The mass times the planet over r squared.
Yeah, because there's like 3 or 4 problems in your problem set that you can answer just by plugging in these numbers into, you have to know what the equation is. G equals gm, mass of the planet, divided by r squared. In a number of your problems, they ask you to find out what the surface gravity is on a certain planet. One of them I read earlier before I got on with you. It's talking about a neutron star. It's a very dense star out in outer space. They said, what is the surface gravity? You use this. The surface gravity can be calculated right here. You just use that same value for G. It can be the mass of a planet. It could even be the mass of a star, like in that problem. You just plug it in. And what would R be? It would just be the radius, right, of that thing, whatever it is. And that will produce a value for what the surface gravity value is right here at the surface. So make sure you have that noted down, because for sure you can answer a number of these. Like 32, you have a reasonably good shot at. Let me go back here. 38. You might have to think about, that's a concept question, 38. So if you increase something by a factor of something, how much does something else change? And I haven't really taught you that yet, so I don't know what your skill is with, that's called proportional reasoning. But my point is, let me, before you go, 40.
I like your background.
What's that?
The one before the lightning one, I like that one.
You like, say, I'm sorry, one more time?
The background before the lightning, before it changed, it was pretty cool.
Oh, my wallpaper. Oh, yeah. And then, yeah, there's a couple at the end here I'm just pointing out. That one, I think you might, if you, because you don't actually have a teacher. Do I have that right? Like, you don't have a classroom with a teacher. Is that right?
No, but I can ask them.
So you do have a teacher. You just don't have a classroom. Is that now more correct?
It's more, it's online.
So you have a teacher. You just don't have a classroom.
Yeah.
Okay. All right. Do you use him? Do you talk with him, or do you communicate with him?
All the time.
Okay, great. All right. So 54 is like completely different than the Ferris wheel problem. But I know that at the end here, there's a couple problems related to like planets. This one here, near Earth orbit, and 46, another one. Yeah, there's all these very subtle things. So do the best you can, but keep working hard, and I'm proud of you. You're doing a great job. Don't give up on it.
Oh.
All right.
Yeah.
All right. What'd you say? Oh.
I said I won't.
Oh, okay. All right. Take care, Jeremiah, and I guess I plan to see you next Thursday.
Yeah.
All right. Sounds good. Have a good night.
You too.
All right. Bye-bye.
Yeah.
All right. Session has ended at 9:07 p.m. on Thursday night, November 10th. Session with Jeremiah has ended.